Okay, so if we review, enolates are formed by removing H plus from the alpha position of a carbonyl compound. Once we make an enolate, they react as nucleophiles, and so they will add electrons to electrophiles. Right? So we've seen that example doing things like SN2 reactions and doing things like alpha bromination. So we have two examples so far of enolate reactions. In both cases, the enolates act as nucleophiles, and we added a new bond to the alpha position. The next reaction we're going to talk about in this video this is actually one of probably the most important reaction that's out there in organic chemistry. This is called the Aldol reaction, and it is another example where we're going to generate an enolate by treating a carbonyl compound with a base, and then we're going to have that enolate act as a nucleophile. The trick to the Aldol reaction is that you can add an enolate to another carbonyl compound, and so let's think about how that's going to work, right? So if I give you two carbonyl compounds, I'm going to give you benzaldehyde as one of them. And I'm going to give you propionaldehyde as, oops, this is butyraldehyde. We're going to have 4 carbons instead. I've just decided. Right? And we're going to treat this with a strong base. And we're going to kind of use what we know of enolates to kind of discern what's going to happen in the aldol reaction. Right? So the first thing we know is that if you take a carbonyl compound plus base, we get, right, an enolate. Now, we've used sodium hydroxide to do other things in the carbonyl substitution chapter. So, right, so we've used sodium hydroxide to add to carbonyls as a nucleophile before. Notice that in this case, because we're using aldehydes, we can't do carbonyl substitution. Right? Aldehydes are not on our waterfall diagram. Right? We have acid chlorides and esters and all that other stuff. If we had an acid chloride in there and we treated it with sodium hydroxide, we'd get a very different reaction, right? You would get a carboxylic acid as your product. But that's not what's happening here. We have an aldehyde, and so instead that means that nucleophile adding to an aldehyde isn't going to do substitution because we don't have a leaving group here, right? The hydrogen is a terrible leaving group, carbon is a terrible leaving group. That doesn't work. So instead we're going to form the enolate, and we know we're forming the enolate because we have a strong base and we have an alpha position with a hydrogen on it, right? Now, we have to take, there are two alpha positions in these two molecules. We have an alpha position here with a hydrogen, and we have an alpha position here that has no hydrogen, right? So the base plus carbonyl compound to make an enolate only works if there is a hydrogen present at this position. Right? There's no hydrogens present at this alpha position because in benzaldehyde, because there are no hydrogens attached to that carbon. That carbon already has 4 bonds. It has 4 carbon-carbon bonds instead of a carbon-hydrogen bond. And so the only thing that we can do, the only way to make an enolate is by removing this hydrogen, making the carbon-carbon pi bond, and pushing those electrons to the oxygen. Right, so step 1, make the enolate. So benzaldehyde remains unchanged. Benzaldehyde plus base doesn't get us anywhere because there's no alpha hydrogen to remove. So instead we just have an enolate. Once again, you're thinking, well, what if I have 2 compounds and each of them has an alpha position that has a hydrogen on it? What then? It's a very good question. A question we're going to answer in a future video, but not necessarily right now. For now, we're going to set this up so there's only one enolate that we can make, and we're going to kind of go at it from here. But there are definitely there are rules that will cover what happens if we have multiple places where we can make an enolate. But for now, that's not what happens, right? For now, we only have one position where we can make an enolate, so we're going to make an enolate at that position. All right, once we have an enolate, the enolate reacts as a nucleophile. It's going to make a new bond at the alpha position. Reform our carbonyl, and now this double bond is going to go attack something. And so the question is, what electrophile is it going to attack? So as you think about this, right, remember that we have talked about attacking carbonyls an awful lot in the past. And so it makes sense that that's what we're going to do here, right? In this case, our carbon, our alpha carbon, right here, is going to end up attacking the carbonyl carbon. And what happens when we attack a carbonyl carbon? We break the carbon-oxygen pi bond, we push electrons to the oxygen and make a new lone pair there. All right, so what does this look like? Now, we've got our original butyraldehyde. We've reformed the carbonyl. At this alpha position, now we have made a new bond. Right? So we have a new bond from this alpha carbon to the carbonyl carbon of benzaldehyde. And now the carbonyl carbon of benzaldehyde, right? The carbon oxygen pi bond has broken. This oxygen has a lone pair on it, and so we end up with something that looks like this. Right? Now there are two parts to this here. We have our benzaldehyde is 7 carbons, right? So we have 7 carbons here. 6 in the benzene ring plus 1 carbonyl carbon. We have all of that right here. Right? Those are our 7 carbons from benzaldehyde. And then we also have the 4 carbons that come from the butyraldehyde. So if I can find my mouse, I'll do that. We also have 4 carbons on butyraldehyde. Those 4 carbons are up here. Right? So just like we've done in a lot of other reactions where we make carbon-carbon bonds, right? We count the carbons on the 2 parts. We did this with the Grignard reaction. We did this with the Wittig reaction. We're doing it again here with the Aldol reaction, right? If you have 7 carbons in one reaction component and 4 carbons in the other reaction component, we're going to end up with 11 carbons in our final product. We just need to figure out how they are connected. But we know, because we're using an enolate, that they're going to be connected through the alpha carbon. So the alpha carbon of the enolate connects to the carbonyl carbon of the electrophile, and we end up with a structure that looks like this. Now, to finish this reaction off, you would then, in workup, have, that's the right color, but whatever, right? In workup, you would have this, you'd work this up with water, maybe a little bit of weak acid, and you'd end up with an alcohol at this position. Right, so we just add water or H+. Right, so work up. And we'd end up with an alcohol. So the aldol products are always going to look like this, or will at least initially look like this, right? You'll have your carbonyl, you'll have your alpha position, and then you'll have the beta position. And the beta position is the position where the carbonyl of the electrophile was, right? And now it's an alcohol. And so aldol products will always be beta-hydroxy carbonyls. Meaning you'll always have carbonyl, alpha carbon, and then carbon with an OH group attached to it, right? So that will always be the pattern of the aldol products. And the reason for that is, of course, that's how the aldol works. We take an enolate, we add it to a carbonyl, right, an aldehyde or whatever, and we get that carbonyl becomes our hydroxy group. And so that will always be at the beta position because we'll always connect the alpha carbon to the carbonyl carbon here. So kind of the takeaway from all of this is that the aldol reaction is the reaction of, is always going to be an enolate plus an aldehyde or a ketone. And the product will be a beta-hydroxy carbonyl. Oops, I can't spell. I got all excited about the X coming up. Wanted to put it in there first. Beta-hydroxy carbonyl. Okay. Let's do a couple of examples really quick. If you take something like cyclohexanone plus, let's do, what ketone can we do? Let's do benzophenone. Right? If you do something like this and treat this with a base, I'll just use sodium hydroxide again. That's a nice reliable base, right? We again look at our alpha positions. We have alpha positions here and here. Neither of these have alpha hydrogens, and so we have to take a hydrogen from this one. So we're going to have this alpha hydrogen be removed. We're going to make the carbon-carbon pi bond. We're going to break the carbon-oxygen pi bond and make ourselves an enolate. Carbon-carbon double bond, oxygen with a negative charge. We're going to remake the carbonyl and then have the alpha carbon here add to the carbonyl carbon here. And our final product will then be something that looks like this. I have added way too many 6-membered rings to this. This is going to be a fun one to draw. Apologies for my terrible benzene rings. Okay. So you have something like this, right? And then under workup, right? So then when you do workup, you'll end up with the beta-hydroxy carbonyl. I guess I'm drawing this again. So you can go make a sandwich or something while I do this. Benzene ring and another benzene ring. There we go. So this would be our final product. And notice that our product again has our alpha position, and then the beta position has the OH group on it. And so if you see this, that will always kind of tell you that this is an aldol product. Okay, so that's the aldol product, that aldol reaction. Make an enolate, react it with a carbonyl, the enolate adds to the carbonyl in order to do that. We still have some unanswered questions about where do we make the enolate if we have choices, which ones do we make? That will be in the next set of videos. We'll start to address ideas of how do we control which one we make, and think about, well, I won't spoil it. Watch the next couple of videos and then you'll know.